Right, I have just started recording, so let me just summarize. I left you last week with some nice numerical questions. It's something that we hadn't done in the previous topics, specific numerical problems. And of course, it's not a tutorial, but nonetheless, we should try our hand at this and we can learn how to use the equations directly by applying them to these specific numerical problems. So in the first one, you were given a test batch of slurry, and then you were asked to scale up 1000-fold, and you were to design the filter press, which in essence means you have to determine how many plates you need, how many frames you need, so that the 1000-fold capacity of the scaled up device can be met. And this is also in some sense an interesting scale up problem, because you're using the small scale lab scale data, which is on a small circular filter whose area was pi d squared by 4. So d was 5 centimeter. And you were given the time to filter that slurry, you were given the cake volume, etc. So T was whatever mu times alpha upon whatever delta P into some density term times square of the uh, filtrate volume divided by A squared, right? Because the medium resistance is negligible, so you have the quadratic dependence. So you were to use that equation. The time is given, so you can find out the all the specific cake resistance which is unknown from that test data, and now you can always use that to find the new filtration time on the large scale device with the large area of filtration that you are giving. Okay, this is the problem that I gave you. I also gave you some other problems. Perhaps we can, for instance, I said that always we don't need to do our setup, operate our setup at constant delta P, and there are other modes of operating it. So what are they? And if I want constant filtration rate, what should I do? Then I left you with another question. What if the cake is not incompressible, as in this example? Okay, but we have to take them one by one. So let's just stick to question one. So there were two problems here. One is you have to find what is capital A, and what capital A you must use in the filtration equation. And secondly, don't forget that what is given to you is the mass in the test filtration. You don't have the volume. Okay, you're not been given the filtrate volume. Everything you have to work in terms of mass. So you have to recast that filtration equation to calculate the specific cake resistance alpha and any other constants that appear in the slope of that, or which you can get from the quadratic filtration time expression. Okay, so that still you have to, nonetheless, you can't directly apply the formula I derived in class. So that requires some thought. And now as to the area of filtration, if you look at the geometry that I gave you from class 1, we have been discussing this of this topic. I mean, I gave you the equipment design, and I showed you how, explained to you in great detail actually, how the plates and the frame assembly is put together and pressurized. Now, what you have to ask is, where is the filter medium kept? Where is the canvas? Where, I mean, see, the cloth is a continuous thing, but if I were to place it over a frame, the filtration, the cloth physically is covering the frame from both the sides. If we look at it from the side view of the plate, the frame, it's not just one-sided, but the filtration is taking place on both sides of that frame. In other words, if I have to worry about the thickness of the cake, the incompressible cake, as cake builds up, you can say that the cake is building up at a rate which is approximately twice. If you were to just take a simple geometrical situation, because the canvas or the filter medium or the synthetic filter medium of the press is on both sides of one frame. Did you understand what I am getting at? The filtration is taking place on either side of a frame. So the strong implication of this is that the capital A value that you must use is not the geometrical area of the plate or the frame, the cross-sectional area, but you must use twice that value. Okay? In those equations, and even in the first part where you have to design the or predict the number of frames and plate, you have to take the value of capital A to be twice the geometrical or the cross-sectional area of a frame or a plate. Because the filtration takes place on both sides of the frame. Okay? So I would say with that knowledge, you should try to work out part A, that is the design of the scaled up press. How do you go about doing that? See, you know the cross-sectional area. I said you double it, and that's the value, appropriate value of capital A to use in the design, or in fact in the general filtration equation. So with that corrected value of capital A, which is twice the geometrical or cross-sectional area, you can find, since you know the thickness of each frame, you can find how much volume it holds per frame. Correct? So you know how much volume in meter cubed per frame or centimeter cubed per frame. You also know how much of the batch of the slurry you have to process. That's in mass 63 kilograms. What about the physical properties of that cake? That was given to you in the test filtration data on the lab scale. It's the same density of the slurry, whatever 0.25 or 245 gram per centimeter scale, because you know the weight of the crystals, and you know the volume of the cake that was accumulated, that was measured in the test filtration, so you know the density. So essentially you can find out the total volume of the cake that is accumulated in the scaled up device. And now you can design how many frames you need to provide so that you are able to process this scaled up 63 kilogram throughput value. Okay, so that is the way you can work this out. So you can try it. Tomorrow, since Sarthak said we can start the presentation from 28, you can follow whatever order you want. I'll be happy to listen. But somebody has to set the ball rolling, you know. So work this part out. Now the second part, I think I asked you to find the filtration time, right? filter the 1000-fold scaled up batch of slurry. So you have to use the test filtration data with the circular diameter filter whose area is just pi d squared by 4, and uh, use the filtration equation there. You know the time as 163 minutes. Find all the unknown alpha and any other uh, parameters, mu, etc. Bunch them together and find the cake resistance from that. But recast that equation now in terms of the mass, because you are given the total mass of the crystals. You are not given the volume. Okay, so that requires some modification to the equation. So once you have the specific cake resistance, you can now apply the filtration equation to the new batch, the scaled up batch. Well, what will the pressure drop be? The pressure drop now, according to the problem, is not the original pressure drop, because you're using some of that pressure to also pump water, no, against the hydrostatic head. So find how much that equivalent of hydrostatic head is, and subtract that from what the feed pump is delivering, and that's the delta P that you have to use in the constant pressure filtration for the scaled up problem. So use the correct A with the doubling that I mentioned. Use the new delta P after subtracting whatever you have to overcome the hydrostatic head of 15 feet equivalent of water. Subtract that, find the new delta P, find the mu alpha, etc., whatever constants from the test data after recasting the equation for mass instead of volume, which requires some thinking. So it's still not solved. You have to think on how to do that. Maybe we can discuss that tomorrow. And then you are ready to solve for the time. And you expect a short time because you're giving a very large area compared to the pi d 5 centimeters squared. You're giving a area of twice into 30 inch into 30 inch, right? So per frame, and so it's a very large area. So work it out, and let us discuss it. There's still some pitfalls in this. So I've indicated you how to go about doing it, and you must take the next step forward. Then the compressibility, I gave you a constitutive equation, which was like an allometric equation, a power law equation. So the exponent S to which the delta P is raised it would be given to you. Typically for our Baker's yeast sample, that's of the order of 0.3. If if S small s to which the delta P has to be raised is 0, then it's an incompressible cake. And if it's 1, that's the maximum limit. Somewhere our systems are in between. But anyway, don't put the value. Solve now. Substitute the new constitutive equation for alpha and resolve the filtration equation and see what dependence on you get, what new equation you get, and that should be valid for compressible cake with this particular way of modeling the specific cake resistance alpha. Then as to going to beyond the constant delta P, you have to really think how to, if the filtration rate is constant, how you should plot, what you should plot on the X and Y axis so that you can get a linearity in that equation, and how the slope will give you, and what the intercept will give you. You have to, don't forget that you have to find V subscript E, and you have to find the specific K resistance alpha. So you have to have a new slope intercept formulation, different from what we did for the constant pressure filtration. So in a jiffy, this is all the stuff that we want to do before you can start your presentations on next Wednesday. So tomorrow we can again take this up. I mean, originally I wanted it started tomorrow, 28th of February, April is my birthday. I wanted to take off actually, but now it looks like that may not be a good idea, but that's okay. I'll be happy to listen to your the first couple groups, whatever. Sarthak can decide the order. I'm open to any order. Doesn't matter. Everybody has to do it before May 5th or so. So, um, if there are any questions on the first question, on the first numerical problem, I can answer. Otherwise, you can try it. And tomorrow, uh, if you have anything, please ask me. I have really indicated as best as I can. I don't know if it's how clear I am, but so important take home message of today's class: the filtration area capital A that you have to use in the filtration equation that we derived 1 by A dV by dt equal to delta P upon etc. whatever is twice the geometrical area. Okay, so that's something that you can't get wrong. Okay, always double it, please. Otherwise, all your design will be wrong. The number of plates and frames will be wrong. Everything will go haywire. Okay, and even then, though I've indicated what you do, still for the specific question that I gave you, there's still something you'll have to recast and think. So it's not cut and dry. You still need to put your head. Okay. So please try it, and I'll be happy to discuss further or indicate you, or and I can give you the answers if you want to check. All right. If we can get through these questions tomorrow, that will be a very nice, because in a way, scale up is also covered. Originally I wanted to cover scale up as a separate topic, but and as I said, I have some very nice case studies on this for centrifugation and other processes, but we can't reach there. We can't possibly do it. But this is also a scale up problem on filtration. So it's all combined in one. So it's not a bad idea to complete this tomorrow. But I think that you have to try it out. Otherwise, it's very hard to follow, for you to follow what I am saying. All right. So let's meet tomorrow if with these queries, if you have tried these problems out, and I will further indicate what the solutions. Maybe I can give you the numerical answers and you can try them out if you haven't done them by tomorrow. And then 28th, it'll over to you, and Sarthak will coordinate.
All right, sir.
All right. Lovely, man. Take good care. Things are quite bad everywhere, so be watchful.
Thank you, sir. You too.
Yeah, all right, buddy. Thank you very much.